Weird side note, a few more guys.
I guess see Gage afterwards if you're interested. When I was doing consulting, we were playing, somebody in our group signed us up to play in this local league. Have I told you this, Jay? We played against this other team, where I would have been the 5th tallest on their team. We got so crushed. Well, pretty much by everybody except for the other team made up of consultants. Our rallying cry is, we could probably do better than they could on a calculus test. That was. All right. Let's try transformers again. We'll hit that miscellaneous topic. So the essence of a transformer is that you have a set of coils, and you'll have some sort of voltage that is changing, presumably an alternating current, so that the current's floating back and forth and the voltage is switching back and forth. So there's some sort of voltage between there, and eventually I'll find a marker that's dark enough. So I have some sort of alternating current, or alternating voltage. And because the voltage is changing, the current is changing. Because the current is changing, the magnetic field inside the coils is changing. And because the magnetic field inside the coils is changing, we are going to be able to induce a current. And we induce the current in a set of other coils with a different number of loops. So just call this the primary and the secondary. Now there are a couple of configurations that can be used, and it depends upon the situation. So a normal transformer, so if you went out, looked at the power lines, and you saw the box up there, and it'd be really convenient if you could see one from here. See it? Yeah, there's one over there across the street, sort of buried by trees. It's a little gray cylinder.
Mm-hmm.
But for the transformers, especially the larger ones, the configuration you'll see is you'll have some sort of metal core, and you'll have this set of primary coils wrapped around one side, and then the secondary coils wrapped around the other one. And that the change in the magnetic flux that's generated here, actually, the metal serves as sort of a guide, and that change in flux shows up on the other side. Because of energy conservation, whatever energy this loses, this gains, or vice versa. If this is gaining energy, this has to be losing energy. Now, in reality, no system is perfect. There's going to be some energy loss, but there is, according to one source, that if this is well designed, there's about 1% loss in the transfer. So, if we look at it slightly differently, look at it from the point of view of power, which is just energy used per time, then however much energy this loses per unit time is how much this gains per unit time. In other words, the power for the primary coils is going to be equal to the power from the secondary coils. And I am assuming an ideal here because it's a board problem. I know that power is equal to current times voltage. That's current from the primary, so there's some current flowing in here, current primary, is equal to current secondary times the voltage of secondary. Since I am doing alternating currents, just from a notational point of view, typically most of the textbooks that I've seen, yours does it a little bit differently. Most of the textbooks for the alternating current for alternating current for alternating current, and voltage for alternating current, they'll use lowercase for the instantaneous value. So I'm just write that down here. We'll do that more. We'll do that more later. And actually, they usually drop the delta too at that point. So the last line I've written there is nothing new. It's just rewriting of what I've just done. All right, so this voltage, I know that the voltage is equal to negative in d5b dt. Where this, since I put the in out front, this is basically the change in the magnetic flux for a single coil. So, for a single coil. And so the change in the magnetic flux for a single coil, for any of the coils, would be the same. That actually is a constant. But go ahead and plug it into there. We end up with this current from the primary times the number of coils of primary times d phi b dt is equal, basically the equivalent for secondary. Again, assuming that the magnetic change in the magnetic flux is the same on both sides, basically within this structure right here, those would be the same. And so we write off when we have a relationship here between the currents, that I primary over I secondary is going to be equal to the number of coils of the secondary coil over the number of coils for the primary. Or perhaps a little bit more interesting, perhaps, if I looked at the same ratio there, IP over IS, using my voltage equation or my power equation over there, we get Vs over Vp. And based upon that is Ns over Np. In other words, our ratio here of voltages is equal to the ratio of turns. And so I can increase the voltage just by having more coils in the secondary than on the primary, or decrease voltage, like you would see over there, by having more on the primary than the secondary.
So would these transformers be from like your power lines to your house? Like to
that one would be right there.
Right.
But the basic transformer is working for all of them. To give some sense here, look at some numbers. So power plant tends to produce it. I was hoping there'd just be a quick standard across the board, but it really does depend upon which state you're in and what the regulations are and how far they're actually transporting the power and so forth. But from the numbers I got from the power plant, they're producing voltages 14,000 volts, or I think it's or 22,000 volts as opposed to 14,000 to 22,000. Couldn't quite get confirmation on that one. So it goes from the Microsoft's invaded everything. It goes from the power plant to the transmission substation, and at that point it gets jacked way up, and those seem to range from 44,000 volts to 765,000 volts. So that's, you're out in the middle of the country and you see the really big wires and the giant metal structures holding it. That's what we're talking about here. And then when it gets closer to the city, it has to go through the power lines. It gets brought back down again to 7,200 volts, from there to 33,000 volts. And then it travels along the power line until it gets to the neighborhood, and then it drops down again to 120 volts or 240 volts. And then it goes into the meter and then into the,
Breaker.
thank you, service panel is what I was trying to think of, and then to the rest of your house. And then you, when you ask your wife, hey, did you turn the power off? Yeah, I turned the power off. So that's the essence of the transformer. And then there's smaller ones. So you have one in your car because you've got 12-volt battery there, then you need to somehow get more voltage than that. You got a step-up transformer to be able to actually get it started.
At what point does like a coil become a solenoid? Like, is it a certain amount of loops per?
I've never seen a formal definition for it. It seems like it's either you've got a couple of coils or you've got a solenoid, and I mean, I could think technically, probably if you had two coils, you could call it a solenoid, but
Okay.
I think the closer it gets to the length being significantly longer than the diameter, that's the point at which
Okay.
it's a solenoid.
How do transformers blow up?
Yeah, 'cause I seen a couple of, well, not blow up, but I remember one time it just blew out of nowhere.
They don't fare well when you hit them with forklifts.
Safety tip?
That's one way.
Drunk drivers at night.
Actually,
Lightning strikes.
you don't fare well when you hit them with forklifts if they're overhead.
Oh, God.
It's just like an imbalance in equals.
I'm trying to think what would cause it to blow up. I mean, so you have electricity running through wires.
Mhm.
So there's resistance there, so you can have heat build up. So if you have too much current flowing through, potentially you could melt the core or something like that. Or, I mean, I don't think it's airtight, so you heat up the air, and potentially the air could blow the thing apart. I mean, I'm just speculating right now. If there's a short and the wire is touching the framework or the casing, would that cause it to explode though?
Probably not explode, but just.
There has to be a resistor in there, that like something.
Are you figuring it's the resistor that blows up?
Yeah, if there's one in there, or a fuse or something. That's what I would, if I was designing one, that's what I would do. I'd put one in there so I only had to come back and place a fuse, not the whole thing.
I don't think you'd want to put a resistor in there,
No.
because the whole point is to try to lose as little as possible.
But where I live, it seems like every time it rains heavy, not even to deal with thunderstorms, we had one blow up.
They probably had hold on paper clips or something like that.
According to the Google machine, it's lightning strikes and heat that causes a spark that ignites mineral oil that's used to keep the transformer cool.
Ah, okay.
Probably
Makes
heat.
sense.
Probably heat.
I had thought about them having something in there that's combustible.
I wonder if that's mainly for underground though, 'cause I don't know that I've seen too much. I haven't seen a container of mineral oil in overhead power lines. I don't know.
So you've obviously run into things like that with forklift, but anybody here actually have any experience with working power poles or power plants?
Besides stealing signs when I was little.
Was that?
Besides stealing signs when I was 16.
I've run three-phase power from a transformer into a building, but never really been around for the connection to the underground power itself.
Trying to think who there's bound to be something on the internet somewhere. Actually, there's bound to be several different contradictory things. Any questions about transformers? All right. Speaking of coils, let's assume that it is a solenoid, whatever that means. We have a bunch of coils here, and we're running current through it. It could be AC or DC, doesn't really matter. I know that as the current changes, so I start out with, I got this coil, I turn on the power, and suddenly I'm going from no current to having current, which means I'm going to go from having no magnetic field to having a magnetic field, which means I have a change in the magnetic flux. If I have a change in the magnetic flux, it's going to create a secondary voltage, which creates a secondary current, which is going to be opposite the direction of the initial current because nature hates free energy. So I know that the EMF that is produced, and I'm not going to worry about the sign right now, is equal to the number of coils times the change in the magnetic flux per unit time. Technically, there's a negative sign there, but it does not matter for what we need. What's magnetic flux?
Integral VDA.
Say it again?
Integral VDA.
And you want to say something?
Same thing.
Now we're talking about the area of a coil here. And so we're talking about the area, basically it's the cross-sectional area. It's basically that open face. You got a circle right there. We're talking about that area right there. The area vector is perpendicular to that surface. So if I have a coil, my area vector could either be pointing that way or the other way. So the magnetic field, so we can plug into here. So I have the number of coils times the integral B dot dA dt. Now we are going to assume a certain ideal nature to it. You can, in not this week's lab, next week's lab, I use a more formal equation for a non-ideal solenoid. But we'll assume ideal, because again, it's a board problem. You gotta start somewhere. So the magnetic field in the middle of the solenoid is equal to mu naught N times the current. The lowercase n is the number of, it's the coil density, number of coils per unit length. So that would be mu naught times the number of coils over however long it is. And I do recommend that you use a lowercase l there, not an uppercase L, because we'll be using that in a moment for something different. None of these are area dependent. So B is constant with respect to the area. So it can come out. And so my formula here becomes N times B, not too far, times D of D integral of dA. Now I did two things there at once. One, I brought the B out, but also I dealt with the dot product. the magnetic field is running along the longitudinal axis of the coil, of the solenoid. Area vector is gonna either point in the same direction or opposite direction. We'll just define A so that it's the angle between the magnetic field and the area vector are in the same direction. So I dealt with the dot product there. So I have an integral of dA, which is,
Right.
and that is not time dependent, so that can pop out. And so I'm left with NA dV dt. Plugging our value for B and our formula for B right there. So we now have NA ddt mu naught N I over L. I think I can write that better. ddt of u naught N I over L. And the only thing that's changing here is the current. I'm assuming that our solenoid is pretty much set, it's constructed, and we build it, and it has a certain length to it, has a certain number of coils. Well, that this is independent of the solenoid itself, pretty much. And so factoring those constants out, I'm left with the area times N squared mu naught over L. Thinking them all, you know, N squared A, just change the order, and then times d I dt. And there's a minus sign there. I probably should have kept it and just carried it all the way through. There's a minus sign. So what do we end up with is this EMF through this solenoid, or this back EMF through the solenoid, is equal to negative times this thing right here. Now recognize what that is, or recognize that it is dependent upon how you make the thing.